the temperature-dependent composition plot. Apparently, the x-axis was actually the composition. The things that's going to change will be your y-axis. Previous, we have the pressure. Right now, what we have is actually going to be temperature. Again, it's going to transition between the liquid and the vapor phase. So the temperature we're going to talk about will be the kind of like the boiling point of your liquid, assuming all the things done at one bar. We still have component A and B is actually more volatile than A. Previous, we actually plot out the PA star and PB star, right? Here, we're going to plot out the TA star and TB star. So remember, previously we say B has higher vapor pressure, so B is easier to vaporize. From that concept, you should know that the boiling point of your substance A should be actually higher than the boiling point of your substance B. You should also know that the phase diagram should be separated into 3 different zones. One is liquid, one is gas, one is liquid gas coexist. So now my question for you is actually zone 1, zone 2, zone 3. Which zone is actually liquid? Zone 3, right? Because lower temperature is going to liquefy. So this will be your liquid. High temperature, of course, will be your gas. And then this will be liquid gas coexist. If you have a chemical composition XB, if you start to increase the temperature of your system, here you actually start with all liquid form. Let's say it's 0.1. 0.1 will be the point you are going to see the first liquid molecule evaporate. And then if you enter zone 2, which is actually coexisting zone, the chemical composition will determine by this and this. This will be your XB. This will be your XBV. Bottom one is the liquid composition curve, and the top one will be your vapor composition curve. So if you keep increasing your temperature to 0.2, at 0.2 you will see the very last liquid molecule evaporate. So beyond that temperatures, for this given composition, everything will start to exist only in the gas form. So how do you calculate your P total? P total, again, we know PA star times XA plus PB star times XB. We can actually replace my XA with 1 minus XB plus PB star times my XB. So eventually I got P total is going to equals to PA star plus XB times my PB star minus PA star. The only thing that's different here is the P total is actually a constant because we actually plot these things at a given pressure. In this case, it's just equals to 1. So once you write these things out, the things that you start to wonder is how come in my equation there's actually no temperature? So how do you actually introduce the temperature into this equation? So those pressure is going to depending on the temperature. Remember when we talk about the phase diagram, we talk about the Clausius-Clapeyron equations. They describe the phase equilibrium between your liquid gas phase. The pressure, let's say, is your PA star over a reference state. Let's say it's actually 1 atm. It's going to equals to negative delta H of evaporation over R 1 over T1 minus 1 of your reference. In this case, will be your boiling point. You can actually rearrange these equations. You can actually express PA star as a function of temperature. You can do the same thing so that you can express your PB star as a function of temperature. Okay, so once you have that equations, then you can actually put it back to here. Then you are going to have a very nice relationship that describe how the temperatures is going to affect the composition in your liquid and the gas form. Even though conceptually it's actually very simple to comprehend that idea. But if you look at this equation, to express your PA star or PB star as a function of temperature, it actually gets quite complicated. So I would ask you to memorize the equation like that. But assume today I tell you I can actually express my PA star and PB star with some simple temperature forms. And you should be able to actually plug this back in to estimate your P total. In order to actually generate this plot, you also need to know the XB is related to your PA star and PB star. You just rearrange this. So you can actually write out your XB as P total minus PA star over PB star minus your PA star. So remember, right now the PA star, PB star has a temperature term in it. From here, you should be able to figure out what is the correlation between your XB and the temperature. So the same thing for your XBV. Okay, this is actually the curve that's on the top. XBV is going to equals to your P total over PB star times your XB. So you use this definition to figure out how the XBV is related to the temperature. So that's all you need to know for the temperature dependence chemical phase diagram. So right now I want to talk about some applications. One most famous application of this temperature composition phase diagram is actually applied to the distillation of our gas. And the idea is actually very simple. So assuming today you have your temperature composition phase diagram. So in the beginning, that the things you want is only be a minor population within your oil. What you can do is actually, at a given pressure, I heat up my oil to a certain temperature. In the vapor phase, I'm going to have a lot more contribution from my component B. I collect the vapor, then I condense it down. Basically come down to this point. Once you condense it down, then in your liquid, you're going to have much higher concentration of B. Then you can do it again. I go to another temperature, evaporate it, condense it down. Then you can repeat this process. So that in your final condensed liquid, it's going to have a very pure component B, starting from your oil, which has very low percentage of B. In the real life, the oil company do is actually they have this distillation tower. Okay, so inside here is actually your oil. And then inside the tower, they have this interesting setup. So they're just heating bars. So what I do is actually I heat up my oil with different temperature. So in the beginning, you heat up this. Some vapor is going to evaporate, and eventually it's going to condense to the first stage of like heating bars. Once you condense it, then you reheat your stage 1. So it's going to evaporate again, and then condense to your stage 2. And you keep doing this, so on and so forth. So by controlling the temperature, then you can actually distill out the specific components that you want from the oil. This approach is actually great because all the things you need to control is just the temperature. So that's actually how these things was applied in the industry.